Hi guys, in this video we're going to be solving problems on combinational logic circuits. The video prior to this, we were able to give ourselves a conceptual introduction to what combinational logic is all about. We solved some nice little word problems at the end. So now we're going to look at two real-world applications of combinational logic circuits and how to design circuits and truth tables that solve those problems. So that's what we're going to be doing in this video. Design a combinational logic circuit for a 3-input voting system that outputs 1 when the majority of the votes is yes. Design a combinational logic circuit. So we know we're designing a combinational logic circuit. That one is certain. For a 3-input voting system. So they've given us a clue. We've got 3 inputs, all right? So recall what we said. If the number of our inputs is n, then the number of our rows in our truth table is going to be 2 to the n. So we have 3 inputs. So output is going to be 2 raised to the power 3. And that's going to be 8. So we're going to have 8 unique cases, 8 rows on our truth table for this problem. And I will show why that makes sense, why that is possible, why that is how it is, okay? The output's 1 when the majority of the votes is yes. So I have a really cute, really fancy way of showing this. So let's say we have 3 people, okay? Let's really get into the nitty-gritty of defining this problem. All right? Person Jack, Mike, and Harry. Okay, that's right. Do Mike a little justice. So let's say we have Jack, Mike, and Harry, and they're each going to vote. They each want to have votes. So there are 8 ways this can go, which is why we did this calculation. We can have nothing for all of them. All right, or let me do 4 zeros, 4 ones, 2 zeros, 2 ones, 2 zeros, 2 ones, 1 0 1 0 1 0 1. So when you look at this what I've just drawn covers every single case that can happen if Jack, Mike, and Harry decide to make a vote. Okay, you could have 0 0 0 0 0 1. So let's say 0 represents 0 stands for no, and 1 stands for yes. Okay, so 0 0 1 0 0 0, but all of them vote no. Only Harry votes for a 1. Only Harry says yes. Only Mike says yes. Both Mike and Harry say yes. Only Jack says yes. Both Jack and Harry say yes. Jack and Mike say yes, and everyone says yes. So these are all the cases that can possibly happen in this situation. So what we need to do is that even though it doesn't look like it, this is our elementary truth table. Okay? What our truth table we're going to form is going to build off of this. So you see how this helps us to perform combinational logic analysis. So it means that our output is going to be 1 when majority of the votes is yes. So what's majority? Majority in this case is going to be 2 out of 3. So look at this. Let's say our outputs let's draw a box, a voting box, okay? And paper comes in, and our output comes out, okay? So output is going to be low. It's only going to be high when majority of the votes are yes. So look for every case where 2 out of our 3 candidates votes yes. So for this first case, both Mike and Harry, we're going to have a 1. For Jack and Harry, as this case, we're going to have a 1. Jack and Mike, and all 3 of them are going to be a 1. So if you fill the rest as zeros, we're going to see that we've done a truth table. So things like this are what makes combinational logic circuits fun to implement. So now we're going to be a bit more formal and say define our inputs as A, B, and C. All right, so we're going to draw the truth table for this. A. Just let's get ourselves a nice table. Okay. A, B, C. Okay, let's really A, B, C and our outputs. Okay. A, B, C and our output X. So where we had Jack, Mike, and Harry, let's represent with A, B, C. So I'll start 4 zeros, then 4 ones, 2 zeros, 2 ones, alternatively. So this method is what I recommend for drawing truth tables. Filling in your 1 terms alternatively. All right. So output X. Remember what we said. When the majority of the votes are yes, so we look, where is the case where majority votes yes? Here, we get high. Here, we get a high. Here, we get a high. And here, we get a high. So fill in the rest at 0. So if you don't understand, we looked at this circuit. We looked at this question. We output 1 when majority of the votes are yes. So to define majority, that means 2 out of the 3 inputs are high. So that's 4 cases. All right. So tada, we have our truth table for this, which is a very simple expression. The next thing we'll do is to write out the basic binary expression for this. Okay. So if we were to write this out, we would say, okay, we used X. So we'll say X is equal to, so look at this case. You have 0, 1, and 1. 0 is the negation of the Boolean. So this is going to be not A, B, C. Okay. Not A, B, C. Let me write this sort of higher. So we have space for table. So X is equal to not A, B, C. Because B and C are high and this is low. The next case, B is low. So we have A, not B, C. Next case, C is low. So we have A, B, not C. And final case, everybody's voting yes. So we have A, B, C. So take note of these steps we're doing when solving Boolean combinational logic circuits. We first of all define the scope of the question even before drawing a truth table so we can get our heads around what's sort of happening. Then we made our truth table. Then we had our expression. Now we're really going to get into the fun part of this, which is drawing the combinational logic circuits. All right. The domain of this function is going to include A, B, and C. Okay. So the of X includes A, B, and C. All right. So we know we're going to have A and their negation, B and their negation, yada, yada, yada. The truth table for this. Recall, we treat the terms one by one. Okay. We design it one term at a time. One sum term at a time. All right. So let's try and see if we can get our hands around not A, B, C. Not A, B, C. So if we say this is the line for A, call this the line for B, call this the line for C. Okay. A, B, C. We need to negate A, so we'll make this a negation. Draw her out. And perform the AND operation on 3 of these guys simultaneously. So that's going to be a really big gate, okay? Should I reduce space to make it more appealing? Okay, so let's see if I can do that. So we have A, B, C. So just so we can have a cuter circuit. So we have a 3 input AND gates, okay? So what's coming out of here? Remember, we negated A, so we have not A, B, C. So it's really as simple as that. You take it term by term, designing the circuit. So let's get to work. The next term is A not B, C. So we can really simply just draw out A over here. So let's bring down A before it gets negated. So we have to be careful of that. Okay. A. We're going to negate B. So have that in mind when you're bringing it down to lead into the gates, that you're going to include a negation. Okay. So we're going to just do that straight up so we don't forget to do it when the time comes. All right. And then C. All right. So we're going to AND these guys. And this output is going to be A, not B, C. So you can see it's really cute stuff. The next is going to be A, B, not C. Ooh. How do we do this? So for terms for space, we can actually draw down the A from here. But let's see how far we can push our luck before this becomes something we can't read. Okay, I'll highlight what we're doing with the junctions so we don't make errors. in where we're bringing our values from. So we have A, B, and we're negating C. So we have to keep that in mind. A, B, and we're going to negate C right before we lead her into the NOT gate. So this is our negating symbol, a triangle, the NOT bubble, and this will feed into the 3 input AND gate. Okay. A, B, not C. And finally, okay, so let's extend this backwards so we have space. Okay. A, B, C come out here. A, B, C. And then the last thing we're going to do is the last term, A, B, C. So we're not going to negate anything. We just bring everyone straight down. Then apply the AND gate. So you can see, although looking at this as a solution on its own may seem mightily complex, as we're walking through this and designing this together, we come to realize that there really isn't much to designing combinational logic circuits. Okay, they perform the AND operation, and then out comes A, B, C. Cute. We have all our terms here, and now we're going to bring them into a 4-input OR gate. Because recall, we have the operation binding all of them is the OR operation. All right, so we're going to do that. Let's bring this out a bit further, then down, somewhere in the middle of 2 of these. So AB not C can come close. AB not C can also get over here, and ABC will get in on the action. So we have 4 inputs here, and all of these will now lead into our final OR gates that will look something like this. Okay. And ladies and gentlemen, we have drawn the combinational logic circuits for, okay, that may not fit in there, for not ABC, not ABC, or A not BC, or AB not C, or ABC, which is our output Y. So you can see it's really cute designing the combinational logic circuits. So usually, to make things more certain, you can highlight the junctions to make sure that you know where your values are coming from. And it may also help to write these out before they get into your gates, so that A not ABC, A not BC, AB not C, and straight up ABC, so that you're absolutely certain what's happening when you're performing your operations. So although this may look, okay, so let's write the combinational logic. Combinational circuits. Okay, so looking at this straight up, like out of nowhere, looking at this, it will definitely seem complex. But now that we've walked through the word problem, designing the logic circuits, we can now see that it really isn't something to be scared of. Let's see if we can get our hands on one more question. Design a combinational logic circuit for a smart home control system that turns the light on when it is dark and there is someone in the room and it is not daytime. So, what's going on here? Design a combinational logic circuit for a smart home control system that turns the light on when it is dark. So the first thing we can establish is that our output is going to be a light bulb. So you can do any sort of diagram that will help you design the circuits conceptually before you jump into drawing a truth table. So a light bulb is going to be either on or off, and this is our output. Okay, very clearly. That turns the light on when it is dark. All right. We now have to look very carefully at the terminology here. That turns the light on when it is dark. And so let's say is it dark? Okay, so let's write this question. Is it dark? All right. Is there someone? Okay. And is it daytime? And is it daytime? Recall in binary, we're going to have 0 or 1. So let's 0 be false and 1 be true. We have 3 terms. So let's get into drawing our conditions. 0, 0, 0, 0, 0, 1, 4 zeros, 1, 2, 3, 4, 4 ones, 2, 1, 2, 1, 1, 0, 1, 0, 1, 0, 1. So let's see. When is our light going to come on? It turns the lights on when it is dark. So the answer to the question, is it dark, has to be yes. So we know that we're going to look at this. Okay. The next term is and. So it is not going to be, is it dark or is there someone in the room? No, it is and. And the and operation is very strict. Recall A and B is only going to be high. 0, 0, 1, 1, 0, 1, 0, 1. A and B is only going to be high when both of these are high. Okay? That's the peculiarity of the AND gate. So now we're only going to be high if every condition met here is true. So is it dark? Yes, that has to be true. So we're only going to be looking at, we're going to keep this in mind. Is there someone in the room? So that has to be true. Is there someone in the room? That has to be true. So looking at the first condition we stated, is it dark? We have 4 cases for this. And is there someone in the room? We have 2 cases where there's no one in the room and 2 cases where there is someone in the room. So we had 4 terms we're looking at, and that got reduced to 2 because it needed to satisfy 2 conditions. It needed to be dark and there had to be someone in the room. The last thing we're going to look at, and it is not daytime. So that means daytime has to be false. So 1 would be, is it daytime? Yes. 0 would be, is it daytime? No. So which of those would it be? 0. So this depends on your terminology, okay? In answering this question, I'll be very explicit as to what means what. All right? So now we can see that our output is going to be low on every case, except when it is dark, there is someone in the room, and it is not daytime. All right? So these are the how do I describe this? These are the conditions you would have to do to make solving combinational logic easier for yourself. Okay, take as much time as you need, be as explicit as you need to be able to design your circuits in a way that's easily understandable. All right, so now I am going to draw my truth table as is required. I have 3 rows of 3 inputs and a final output. All right. So now I'm going to be introducing variables, and in solving questions like this, I would be very explicit. All right. Turn on the light when it is dark. All right. So dark, 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 dark. So let's call this R. So R would be, is it dark? Okay. So I'll call this R. So in solving this, I would write this out so as to not to be explicit in my solving. All right. So that's R. Is there someone in the room? So S would be, is there someone? And it's a question because the answer to this question is going to be either true or false. That makes it binary. And is it not daytime? So D is it day. So let's call that D. And our alpha is going to be alpha light. So filling our truth table, 4 zeros, 4 ones, 2, 1, 2, 1, alternating between 0 and 1. Recall the hard work we did. Is it dark? So remember R is for dark, as these 4. And is there someone in the room? So that has to be true, leaving us with these 2. And is it not daytime? That has to be, is it not daytime? If it is day, that means day will be 1. And if it is day, that means it can't be not day. So that has to be 0. Okay? If I made my variable n for is it night, the answer to this question, if it was 1, then that means I would work with 1, 1, 1. Is that clear? Because not daytime means it is night. But I'm working with is it day, and that has to be, the answer to that question should be false false, so I can turn on my circuit. So I'm going to write this as my sole 1. Then fill everything as low. And like so, I have filled my truth table. Getting into the combinational logic circuits, recall we have to write out the expression for every term where our output is high. So L is going to be R, S, not D. Cool, because we have 1, 1, 0. Join this. Let this be R. Let this be S. And let this be D. Okay? R, S, D. We're going to have to negate this, so keep that in mind. And our bubble in front. Okay? So D comes in, not D comes out. Alright? Then all of this is going to enter our AND gates. Okay? You have to be really intentional when solving these kind of questions. Alright? Because looking at our final expression is L is equal to R, S, and not D. Okay? It is an AND operation joining these two. Cool. So you're now going to introduce our AND. That's really wobbly. We're going to introduce our AND gates. And that, my friends, is all the work we have to do. R is here, S is here, not D is here. So this is RS, not D. So that is the combinational logic circuits for this seemingly complex question. So as you can see, as you solve more problems on combinational logic, you get to see that once you're able to relax and explicitly define your questions, draw your truth table according to your definitions, understanding the question, you'll be able to easily draw your output. In the next video, we'll get into solving. I think there are more complex word problems we can attempt before we head over to sequential logic circuits and handling digital electronics fundamentals. Thank you for watching, and I'll see you in the next video.